Right, we're about to embark on the third walk. Today's walk will span about 80,000 light years. In other words, filling a sphere 160,000 light years across, about the width of the Milky Way, but with the Sun at the centre. We will encounter nebulae, a supermassive black hole, the nearest satellite galaxy, and of course billions of stars. I've picked a handful of stars that you can see in the night sky. You'll notice the further we go, the larger and hotter the stars get. Obviously, no such relation exists in the real world. My selection criterion is biased. Specifically, it suffers from Malmquist bias. The brighter something is, the more likely it is to be selected. This is a trivial example, but Malmquist bias exists in the real world as well. We'll talk a bit more about this on a future walk. Yesterday's walk, the Oort cloud and the nearest stars, fills a 1 metre wide beach ball, 16 light years across. The walk before, the solar system we know and love, the planets, the asteroids and the Kuiper belt, is 100 microns across at this scale, a speck of dust. The Sun, meanwhile, is 10 nanometers across at this scale, the size of a protein. Let's look at the nearest stars. At 50 centimeters, we come to Wolf 359, a red dwarf, the smallest, coldest, least massive, and most common stars in the universe. They account for maybe 3/4 of the Milky Way galaxy. Wolf 359 is an M65 star. I'll explain what this means a little bit later. At about the same distance, we have Sirius, a binary system composed of Sirius A, an A05 star, a little bit bigger than our Sun, and Sirius B, a white dwarf. I'll explain what those are a little bit later as well. At just under 2 meters, we come to Vega, 20 nanometers across, the size of a rhinovirus, twice the width of the Sun. Like Sirius A, Vega is an A05 star, but it spins once every 12.5 hours, and as such, is 20% wider at the equator than it is at the poles. Between 2 and 5 meters, we see 3 red giants, Pollux, at this scale 88 nanometers across, the size of the adenovirus, Arcturus, 1/4 of a micron across, the size of the smallpox virus, both K03 stars, and Aldebaran, just under half a micron wide, the width of a small bacterium, a K53 star. Taking our first steps, we get to Achernar, 120 nanometers across, the size of the coronavirus. Achernar is a B65 star, a blue main sequence star. Achernar spins once every 50 hours, and it is nearly twice as wide at the equator as it is at the poles. At 21 meters, we get to Canopus, 710 nanometers across, the width of a bacterium. Canopus is an A92 star, a blue bright giant. At 30 meters, we get to the Pleiades, otherwise known as M45 or Messier 45, the most famous open cluster in history. The Pleiades is 70 centimeters across at this scale. The Pleiades is about 100 million years old. It is an open cluster of young, very hot blue stars that are short-lived. These stars form together in the same nebula, and we'll talk about nebulae very soon. At 50 meters, Betelgeuse, 9 microns wide. That's 900 times the width of the Sun, the size of a red blood cell or ultrafine aerosol. In October 2019, Betelgeuse dimmed considerably to 1/3 of its typical brightness. Astronomical record shows this has happened in the past. This is evidently not unusual for Betelgeuse, which dims at intervals for some reason, but no one knows why. Bit of a mystery. Maybe one day we will know. Betelgeuse is the 10th brightest star in the sky. It is an M11 star, a red supergiant, and very close to the end of its life. At 60 meters, we get to Rigel, 800 nanometers across, the length of a bacterium. Rigel is a B81 star, a blue supergiant. The 7th brightest star in the sky, it is also very close to the end of its life. It will soon explode in a Type II supernova, at which point Rigel will be the brightest object in the sky after the Sun and the Moon. At 90 meters, we get to the Orion Nebula, at this scale 1.6 meters wide. The Orion Nebula, also known as Messier 42, is visible to the naked eye on the handle or sword hanging off Orion's belt. It is 24 light years across, that's 6 times the distance from our Sun to Proxima Centauri. Nebulae are enormous. Orion is what is called an H2 region, a vast cloud of molecular hydrogen. The hydrogen clumps together to produce short-lived blue stars, like in the Pleiades, that emit UV radiation, which in turn ionizes the cloud of hydrogen, making it glow. Before long, after some millions of years, Orion will coalesce into a star cluster, just like the Pleiades. At 170 meters, we get to the center of the Orion Arm. The Orion Arm is our tiny spur in the Milky Way. It's 240 meters wide at this scale and 680 meters long. At 260 meters, we get to VY Canis Majoris, which is 14 microns across at this scale. That's 1,400 times the width of the Sun, the size of pollen. VY Canis Majoris is an M31 star, a red hypergiant, one of the largest known stars in the universe. Between 260 and 400 meters, we have three more nebulae: the Lagoon Nebula, Messier 8, the Omega Nebula, Messier 17, and the Eagle Nebula, Messier 16, which includes the Pillars of Creation, each about the size of a vehicle lining up at these traffic lights, and all of them visible to the naked eye in the night sky. At 420 meters, we get to the Wild Duck Cluster, and the Wild Duck Cluster, otherwise known as Messier 11, is 13 meters wide. It is one of the most massive open clusters we know of. Like the Pleiades, it is filled with young, very hot blue stars, about 300 million years old. The Wild Duck Cluster will disperse inside a few million years. At 580 meters, we get to the Carina Nebula, which at this scale is 31 meters wide. It is enormous. It is one of the brightest nebulae in the sky, and it is visible from the southern hemisphere. It's also incredibly rich. It includes the Defiant Finger, the Mystic Mountain, and the Homunculus Nebula, at the center of which is Eta Carinae. Eta Carinae is a highly variable supergiant, which from 1827 through the early 1840s underwent the Great Eruption, during which it was brighter than Rigel. The Great Eruption ejected huge volumes of gas, which now form the Homunculus Nebula. We've got a bit of a walk to do to the next thing, so while we're doing that, let's talk about stars. When I say that Wolf 359 is an M65 star, what does that mean? M65 is the star's spectral classification. In the Morgan-Keenan system, a spectral classification has two components. First, a spectral class composed of a letter and a number. The letter, from hottest to coldest, is one of O, B, A, F, G, K, M, with further letters for things like brown dwarfs. And the number, from hottest to coldest, is 0 to 9. It's worth pointing out that temperature corresponds to colour. From hottest to coldest, blue, white, yellow, orange, red. And second, a luminosity class, which is a number in Roman numerals, roughly meaning size, from largest to smallest, 0, 1, 2, 3, 4, 5, with further numerals for things like white dwarfs. 5 is the main sequence, that is, stars fusing hydrogen into helium in their core. It accounts for, by far, the vast majority of stars in the universe, including our own Sun. Anything less than 5 is a giant. So let's talk about giants. When I say Pollux, Castor, and Aldebaran are red giants, what does that mean? A red giant, in a word, is any star on the red giant branch. Red giant branch stars are former main sequence stars that are near the end of their life. When you fuse hydrogen, you get helium, and given enough time, about 10 billion years for a star the mass of our Sun, helium collects into an inert core around which hydrogen fusion continues in a shell. The outward pressure force rises very rapidly, and the star grows in size very rapidly along with it. But the surface temperature does not rise, and as a result, you get a red giant. Our Sun will turn into a red giant in about 6 billion years. Here we are at 1.8 kilometers, the center of the Milky Way. At this scale, 11.5 kilometers wide and 13.5 kilometers long. At the center of the Milky Way, as at the center of most spiral galaxies, there lies a supermassive black hole. Ours is called Sagittarius A star. Its mass is probably about 4 million times that of the Sun. Its event horizon is probably about 60 million kilometers in diameter, less than half of one astronomical unit, about half a micron at this scale, a bacterium. In other words, the size of Aldebaran, a red giant. Aldebaran, for comparison, is less than twice the mass of the Sun. What is a black hole? I think the easiest way to understand it is like this. On the second walk, we talked briefly about the Sun's Hill sphere, the point beyond which an object cannot possibly orbit, as the requisite orbital velocity is 0. Anything passing at that distance cannot be captured by the object's gravity. But there is an inner limit as well, called the Schwarzschild radius, where the requisite orbital velocity is the speed of light. Anything inside that radius cannot escape the object's gravity. Almost all objects in the universe, obviously, are themselves larger than their Schwarzschild radius. The ones that aren't are black holes. A black hole's Schwarzschild radius is also known as its event horizon. Anything that crosses the event horizon is never seen again. Let's talk a bit more about stars. When I say Betelgeuse is a red supergiant, what does that mean? After a Sun-sized main sequence star forms a helium core and enters the red giant branch, it will, after about 1 billion years, begin to fuse helium in the core, at which point it enters the horizontal branch. After about 100 million years, a new inert core of carbon, nitrogen, and oxygen forms, and the star begins to fuse helium in a shell, like it has already been doing with hydrogen. At this stage, again, the outward pressure force rises, and the star enters the asymptotic giant branch. Again, it grows very rapidly and cools at the surface, and you get a red supergiant. Such a star is very close to running out of fusible material. It will live maybe another 10 million years before it simply stops burning, at which point you have a white dwarf. When I say Sirius B is a white dwarf, what does that mean? A white dwarf is a stellar remnant or corpse, in a word, the star's core. Almost all stars in the Milky Way will end up as white dwarfs. It's the size of Earth, but it's the mass of the Sun. In other words, an extremely dense object, specifically a dense plasma of unbound nuclei and electrons. So dense, in fact, that 1 ton of white dwarf fits in a matchbox. If the white dwarf is the star's core, what happens to the rest of the star when it burns out? Good question. At the point a Sun-sized star nears the end of its life, it has grown so large that its gravity is not strong enough to hold it together. The outer gas envelope of the star disperses into a cloud of molecular hydrogen, also known as a nebula. Thus, the story begins anew, in the stellar circle of life. But, I hear you ask, we passed all these things ages ago. Why am I telling you all this now instead of explaining as we went along? The answer is, very simply, because the video would be too long if I did it that way. Guess you'll just have to watch it a second time. At just shy of 4.8 kilometers, we get to Sagdag, the Sagittarius dwarf elliptical galaxy. It is 680 meters wide at this scale. A satellite galaxy is a galaxy that orbits another one. In this case, Sagdag orbits the Milky Way. It is probably the nearest galaxy outside of our own. At the center of Sagdag lies Messier 54, a globular cluster. Evidence suggests an intermediate mass black hole lies at the center of Messier 54, in other words, at the center of Sagdag. There are a few more galaxies up the road here, but we'll talk about them next time.